Early on I asked you where thermo appears in the real world, and I suggested to you that it was race cars and cold beer, right? Well, so hopefully now you've seen the race cars part, basically how engines really work and what they really do, and that is simply convert heat or thermal energy into work. That's the main goal. That's one of the primary goals of the study of thermodynamics, is this conversion and doing it efficiently. The next part is the cold beer. What about that? We haven't heard anything about cooling down food for transportation or keeping things cold. There are lots of medical processes that depend on pure gases and things, so how do we cool things down? Well, we're only going to study one refrigeration cycle, and we'll start by considering if the Carnot cycle would work as a model for refrigeration, because all refrigeration really is the reverse of a heat engine. Instead of taking thermal energy and making some of it into work, what this does is it takes work and moves thermal energy from a low temperature source to a high temperature source, and of course that work is all converted into thermal energy in the process. So what if we considered a reversed Carnot cycle? So a Carnot cycle that produces work would be rotating clockwise on a TS diagram. So a counterclockwise rotating cycle of any type would be a heat pump type of cycle, something that requires work input but produces flow of thermal energy from a low temperature area to a high temperature area. Now you know that won't happen on its own, so we've got to have some type of device to make this work. So if it's a reversed Carnot cycle, let's begin at the compressor. So from state 2 to state 3, where there was a turbine before on the right hand side for power production, now it is a compressor for compressing whatever the working fluid would be. So we go from state 2 to state 3. State 3 to state 4 would be a heat rejection to the higher temperature sink. Okay, so from 3 to 4 we'd have heat rejection at a higher temperature. So that would just be a heat exchanger. From state 4 to state 1 would be, ideally we'd use a turbine here so we recover some work, although of course the net effect is that we have to put work into this cycle. But from 4 to 1, the turbine would produce some work, allowing the fluid to go from a relatively high temperature, relatively high pressure to a lower pressure, lower temperature fluid. And then of course that fluid would have to go through the evaporator to go from having so much liquid. To state 1 has a very high percentage of liquid since it's so far to the left, so close to the saturated liquid line. But then we could move, by evaporating and pulling in thermal energy from a cold medium, we could evaporate off some of the gas so that we end up in state 2, where there's a higher percentage of vapor and not so much liquid anymore. Now this is not very practical for the same reason that the Carnot cycle itself was not practical for a work-producing vapor cycle. Understand that we're still talking about refrigeration here, and most refrigeration cycles involve vapor, so something that can go back and forth between liquid and gas. That's why we're still playing around with the vapor dome here. So often what happens is the working fluid goes back and forth between vapor and liquid phases in refrigeration. It's the case in your car, that's the case in your air conditioner, if you have a heat pump, even if you have a geothermal heat pump. That's what happens. The working fluid goes back and forth between vapor and liquid. Now if you have an air conditioning system in an aircraft, it may not involve a liquid. You can actually have a gas refrigeration cycle simply using air. They're not necessarily the most efficient, but sometimes on a plane it's better to be able to fly than to have extremely high efficiency, right? And so things have to be light, and these compressors and turbines and things cost a lot of weight, if you will. And so especially the type that are practical to use when the working fluid goes back and forth between gas and liquid. So this Carnot cycle, though, this reverse Carnot cycle, doesn't look very good for the same reason that it didn't look very good for power production with a vapor. And that is because of the turbine and the compressor. You can't find devices that would either compress a mixture of gas and liquid to, say, just a gas, and you can't find devices like this turbine that would expand just a liquid to a mixture of vapor and or gas and liquid. So that's the impractical part of this. So the heat addition and heat rejection parts are no problem. Those are just heat exchangers, since we're talking about boiling and condensing processes, making those occur at constant temperature. That's easy. It's again the 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 vertical processes that are not practical. So the reverse Carnot cycle simply is not very good for refrigeration. What we use instead is something called the ideal vapor compression refrigeration cycle. Like I said, this is not the only refrigeration cycle, but it's probably the most common, so it's the one we're going to study. So what we're going to do is something kind of like what we did with the Rankine cycle. We're going to move the compression outside of the vapor dome so that the compression can all occur in one phase. In this case, it's occurring in the it says it's moving to the right. I mean, it has to occur in the gas phase, and so that's a gas compressor. So from state 1 to state 2 is a move through isentropic compression. Again, we're assuming an ideal compressor so that the working fluid goes from a relatively low pressure, low temperature state, state 1, up to a high pressure, high temperature state at state 2. And since it's at a high temperature, we can then run it through a condenser. It's now at a relatively high temperature, so we can cool it down even if we're talking about summer air being the cooling medium, because even though the summer air may be 100 degrees, the refrigerant's going to be up to 120, 130 degrees or so, and so heat will flow from that refrigerant to the outdoors. So state 2 comes down, cools down to the vapor dome you see there. There's no state number, but it continues to cool all the way to state 3. So it's really important to have an appropriate pressure so that the temperature of the refrigerant remains high enough so that whatever the outdoor temperature is in the case of refrigeration is still low enough that heat will transfer from the refrigerant. So state 3 still has to be at a temperature above the outdoor temperature. And of course the systems are designed to operate that way, so it's not really a big concern. So anyway, from state 2 to state 3 is heat rejection in an outdoor coil. If you've looked at the air conditioner on your home, you've probably seen the outdoor coil, the coil that takes refrigeration or refrigerant that's hot and cools it down with hot summer air, because the hot summer air is at a lower temperature than the refrigerant. And so the point here is that refrigeration cycles don't generate cool. What they do is they pump heat. You can't destroy the thermal energy. You have to move it. You have to take it and move it to a higher temperature. And a lot of times people really struggle to understand that there's a difference between thermal energy and temperature. Yeah, thermal energy is related to temperature, but there's a difference between the two, and heat is yet its own thing again. So anyway, from state 3 to state 4, before we were thinking with the reverse Carnot cycle of having some type of turbine where we could get work back out, but what we're going to do instead is just forgo that. Since the goal here is to drop the pressure, we're just going to use some type of flow restriction, an expansion valve of some type. And so while ideally we'd like to have a turbine that operates isentropically, so state 3 would move straight down to state 4' on the TS diagram, rather what we're going to do is simply allow some sort of uncontrolled expansion. What that means is that entropy will be generated in the expansion valve, or whatever throttling device we have, whether it be a capillary tube or a set valve or a thermostatic expansion valve. But anyway, 3 to 4 is going to move to the right on the TS diagram because the entropy is increasing. This is an irreversible process, so we expect to generate some entropy in that process. So we actually end up on state 4 instead of 4', and basically sacrifice a little bit of efficiency, because most of the time the cost of the turbine is just not worth it. Our main goal is to keep the meat in the refrigerator cold, right? We're not really trying to make it the most efficient, since it doesn't necessarily draw that much power by comparison to what it could draw. So from state 4 to state 1 is the evaporator. This is the business end. This is the whole reason for doing all this, right? This is the coil that's either inside of the refrigerator, or in the case of your home air conditioning system, this is the coil that's in the ductwork that has cold refrigerant running through it so that the air in your home can be cooled down. So from state 4 to state 1, what happens is we move from state 3. Let's start it before the expansion valve. We have this saturated liquid and we allow it to expand. Well, when it expands, some of it boils off. We're just dumping the pressure. So some of it boils off. That's how we end up at a state 4, that has still some liquid but a decent amount of vapor in it. And so at state 4, we still have some liquid that can boil off. So typically these refrigerants are down, around 50 degrees if we're talking about a home refrigeration system, or I shouldn't say that, a home air conditioning system. So state 4, there's still some liquid, in fact quite a bit of liquid, available to be evaporated. So this is relatively low pressure, low temperature refrigerant that's ready to absorb heat from the air or take on thermal energy because it's at 50 degrees. So 70-degree air in the home can easily give up thermal energy to this refrigerant in a heat exchanger that's inside of your ductwork. And so if you've ever seen an A coil, for example, that's how it works. That's the evaporator. And its job is to absorb thermal energy from the surrounding air, put it into the refrigerant, and in the process boil off that refrigerant. So there's always a sort of a gas check so that liquid remains in the evaporator and only gas is allowed to escape the evaporator, because if there's still some liquid, that liquid still has a significant potential for being boiled off and for refrigeration. So it doesn't make sense to allow liquid to continue on into the compressor. Also, if you did, the compressor could be damaged, because these compressors are not designed to work with liquid. They're designed to compress only compressible things, gases. So state 1 always comes out pretty close to a saturated vapor, and that's what we'll assume is in our idealized process, is that state 1 is on the saturated vapor line. And then what we're really interested in are coefficients of performance. We're not interested in thermal efficiencies. Thermal efficiencies don't apply to refrigeration, right? Thermal efficiency is something we use for work-producing devices. These are work-consuming devices. And so if it's set up to be a refrigeration unit where the whole goal is to keep a cold space cold, then we'll use the coefficient of performance for refrigeration. If it's a heat pump and the goal is to keep a warm space heated, like right now it's relatively cold outside, my heat pump's running, and so I'm trying to keep my home warm, I would be interested in the coefficient of performance of the heat pump in that case, right? In the summertime, my unit switches over and operates as a refrigeration device or an air conditioner. In that case, I'm interested in COPR instead. But anyway, these are our measures of efficiencies rather than thermal efficiencies. Now, we don't typically use PV diagrams with these vapor compression refrigeration cycles. Rather, we use pH diagrams, pressure versus enthalpy. And the reason for that is that the expansion valves are typically assumed to be isenthalpic. What that means is that the enthalpy at the entrance and exit are the same. So state 3 and state 4, you'll notice, against a horizontal enthalpy axis is a vertical line. And the state 1 to state 2 is obviously going to increase enthalpy because we're putting work into a fluid, right? So that fluid's enthalpy is going to increase. It's also nice to see it this way because the condenser and evaporator are, to a good approximation, constant pressure devices. They're just heat exchangers, just open pipes essentially. And so the diagram makes a little more sense on a pH axis set. So this is a case where we've got, in fact, this is the only type of cycle where we use a pH diagram. Now, pulling the cycle and the pH and TS diagrams over to this page, again, you will want to mark these pages in your book. And here are some equations that you'll want to add. The power input to the compressor is equal to the mass flow rate of refrigerant through the compressor times the enthalpy change of the refrigerant across the compressor. That's an equation you need. That's a good equation for the compressor, for the process from state 1 to state 2. Also, ideally, this compressor is going to operate isentropically, so the entropy at the entrance and exit of the compressor would be equal. Another equation that's useful for the evaporator is that the heat transfer rate into the evaporator equals the mass flow rate of the refrigerant as it moves through the evaporator times the enthalpy change across the evaporator. Now understand, we assume that these things operate at steady state, and so the mass flow rate through the evaporator equals the mass flow rate going through the compressor as well. So when you see it just labeled as m dot, that's all it is. It's just a mass flow rate. Now, another equation that's useful is the heat addition rate in the condenser. The heat addition rate is the mass flow rate multiplied by the enthalpy change across the condenser, because the condenser is going to give off energy, right? And so the enthalpy in state 2 will be higher than the enthalpy in state 3, and then that's the heat transfer rate coming out of the condenser. Notice that the majority of these equations are energy balances, and they're all useful. The energy balance for the expansion valve is trivial. It just says that the energy is conserved. It doesn't really change. Now technically it does change form a little bit. Remember that we go from a high temperature, high pressure refrigerant to a relatively low temperature, low pressure. And since there's a drop in temperature, you might think, well, it lost some energy. No, it changed energy forms. Remember, enthalpy consists of internal energy and flow energy. And so what's really happening is a trade-off between flow and thermal energies. But the enthalpy, which is the sum of the two, remains constant across the expansion valve. Now, all these equations are worth writing down around the cycle diagrams, and you should definitely do it. Pause the video if you have to. It's well worth it. Some other useful things to know about this cycle is that the enthalpy and entropy at state 1, since this is a state that is on the saturated vapor line, all you got to do is look up those properties at the pressure of the evaporator. So the evaporator pressure P1 is equal to the pressure coming into the evaporator at state 4. So if you're given either of those pressures, then you can look up the enthalpy and entropy going into the compressor immediately. Similarly, point 3 or state 3 lies on the saturated liquid line, and so the entropy there and the enthalpy can be looked up as the entropy and enthalpy of saturated liquid at the condenser pressure, or P3. Now, heat pumps are often made, in fact, I've never seen a heat pump that was not also an air conditioner, because the way you set up a heat pump is so similar, and the devices required are so similar to what's needed for an air conditioner. All you have to do is add a fairly simple device to make it both, and that device is not all that expensive. So, as I said, the heat pump I have operating has this device. And to change the system from heating to cooling mode, all I do is flip a switch, and what that does is change this valve, which is called a reversing valve, from the heating mode to the cooling mode, and of course vice versa. So let's trace around the cooling mode first, since most people think of air conditioning when they think of these vapor compression refrigeration systems. And of course this is the type of system that's used in your refrigerator too, to keep your groceries cold. So let's start at the exit of the compressor, the purple line. At the exit of the compressor, we're going to have a relatively high temperature and high pressure refrigerant. That's going to go through the reversing valve horizontally over to the outdoor coil. So we're thinking of this as your air conditioner in the summertime. Now remember, this is a refrigerant that is at high temperature, high pressure. Of course, it is a gas. It's a superheated gas. So it goes through the outdoor coil, and it is cooled. All right, so its temperature drops, but it drops to a point where it starts to liquefy out. As a matter of fact, there's a trap on the end of the outdoor coil to prevent anything but liquid from going on through that black arrow. So that black arrow is all saturated liquid that is still at a relatively high temperature and pressure, but it's lost a lot of energy because it went from a vapor to a liquid. So then you see that black arrow coming over horizontally at the bottom of the screen, and remember, it's a high temperature, high pressure liquid. Then it goes through an expansion valve, and that expansion valve allows the pressure to simply drop. So there's a transformation between the thermal energy, or the temperature, and the flow energy. Some of the fluid boils off, and the temperature drops drastically. So coming out of the expansion valve is a very low temperature and low pressure refrigerant. Now that low temperature refrigerant can be used for cooling the indoor air, so it picks up heat. Understand again that we only allow vapor to come out of this, so that the liquid that has potential for more cooling remains in the coil until it is evaporated. And then you see it go through the reversing valve horizontally along that gray line back to the compressor, so that it's only vapor going into the compressor, or gas, and then the compressor completes the cycle we considered. Now think about the reverse operation mode, the heat pump operation mode at the top. Notice that all the valve has to do is turn, right? All it has to do is connect the pipes differently. And that's exactly what it does. Now what happens, like what's happening literally right now in my home, is high temperature, high pressure gas refrigerant leaves the compressor and goes directly to the indoor coil. Since it's at a relatively high temperature, what happens is the indoor air cools it down, or another way of saying that is that the indoor air warms up. That's what I need. It's cold outside. I want to warm up my house. So the refrigerant then has lost some energy, and of course the indoor coil, what it has to do now is prevent anything but liquid from leaving. So It's interesting because in cooling mode, going back to the lower figure, the outdoor coil is called the condenser and the indoor coil is called the evaporator. But in heating mode, what's going on is the indoor coil is actually condensing. So the condensing coil is inside, the evaporating coil is now outside. And so it's a little bit confusing, in terms of terminology, because they've traded spaces, right? They've traded functions. And of course, there's a few more things besides the reversing valve required to make the heat pump operate as well as the refrigeration unit, because you have to have controls for the reversing valve. Plus, you also need it's more practical than to have another expansion valve indoors and then one outdoors. So in most practical heat pump systems, there are two separate expansion valves, but that's a detail that doesn't matter for our consideration. So let's continue going through the heating mode of operation. We came out of the compressor with a high temperature, high pressure gas, went through the reversing valve to the indoor coil, and the indoor coil only allows high temperature, high pressure liquid to leave and go along that black line to the expansion valve in the upper figure. The expansion valve does exactly as it did before. Some of the refrigerant boils off, goes into the vapor phase, but the pressure and temperature of the refrigerant drop significantly. So now, even though the outdoor temperature may be 30 degrees, if the refrigerant is at 20 degrees, it's going to pick up heat from the outdoors. Now you can say, well, there's no heat outside. Yes, there is, because what you really mean by heat is thermal energy, and there is still thermal energy outside. The air molecules are still zipping around, right? They still have energy, and we can extract some of that energy and use it to pump up its quality, in other words its temperature, and use it in the home. So what the outdoor coil does is it takes this mixture of vapor and liquid and it completes the boiling process. And so what happens is the outdoor air gives enough energy to the refrigerant to boil off the remaining liquid, which all goes to vapor and then goes through that upper gray line back to the compressor to complete the cycle. So this is how a heat pump works, and it's a fairly simple thing. Now, there's a couple of problems with heat pumps. Number one, they have a bad reputation because when they first came out, they were designed to be extremely efficient, in order to be a selling point. And what that really means, what that converts into, is that the indoor coil is dealing with a refrigerant, a high temperature refrigerant that's not at that high of a temperature. So if you stand over your register with an older heat pump, it feels like cold air coming out. It's not. It's actually 85 degrees or so, but as it blows past you, since you have water on the surface of your skin, it feels cold. And people just didn't like heat pumps because it felt like they were cooling the house, not heating them. If I put my hand over my register here, I can feel that the air is lukewarm. It's not really hot. It's not like a gas furnace or my wood boiler, for example, where the air coming out of the register is just this really nice hot blast of air, so that when you walk in from outside, it's 20 degrees outside and you can stand over the register and it feels great. The heat pump's just not like that. And one of the reasons is that you want it to be efficient. Now, modern day heat pumps do generate higher temperature air so that people can feel a little more comfortable about it, and they do use some different refrigerants. For example, older heat pumps use R22. My heat pump uses R640A, I think it's called. I don't remember the number right now, but it's a more modern refrigerant. It's something that has a little bit better properties, so it can still be efficient and yet give you a little bit warmer air out of the register. Another problem, though, the biggest problem with heat pumps is, think about that outdoor coil. I kind of glossed over it where I said, the refrigerant maybe is at 20 degrees and it goes through the outdoor coil, the outdoor air boils off the remaining liquid. Well, wait a second. If we're talking about 20-degree refrigerant outside and there's air outside and that air still has some water in it, right, in the form of gas, what do you think is going to happen to that water? If you guess that water is going to freeze on the outdoor coil, congratulations, you got it. That's the problem. Sometimes I put my hand over my register here and it feels really cold. I can tell we're not talking 75-degree air, we're talking 50-degree air or so at the most. Well, the reason for that is heat pumps have an automatic defrosting cycle, because when you form ice on the surface of that coil, you've got to get it off to continue the cycle. And so they literally turn the heat pump into air conditioning mode in order to defrost. Now, I programmed my system custom so that air goes across the indoor coil to make the defrosting happen really quick. I probably should change that because the heat pump's probably a pretty dumb one that just times defrosting, ever so often. But in most heat pumps, when they're set up correctly, the indoor blower does not blow. What happens is some heat is extracted from the indoor coil in order to defrost the outdoor coil, but you don't blow air across it so that people don't feel like you're air conditioning their homes in the wintertime. So it's interesting. These devices are useful. They are very efficient. They certainly are better than taking electricity and simply converting that electricity into thermal energy in the home, because, I mean, what's the efficiency of just a coil of resistance heater? It's 100% efficient. Well, that's actually not good enough, because you can actually take thermal energy from the outdoors, pump it up to a higher temperature, and put it in the home. And instead of taking a kilowatt and converting it into heat in the house, drive that, I should say a kilowatt hour. You can take that kilowatt hour, drive a heat pump, and move 3 units of thermal energy into the home instead. Well, that's what the coefficient of performances are all about. And it's helpful to understand these topics in thermodynamics so that you can select good systems that are efficient and useful and save you money and increase your efficiency, which is a good thing.